So our goal today is to talk about some applications of the Fundamental Theorem of Calculus. So in the previous session we learned about a nice way to compute definite integrals as long as we can find ourselves an antiderivative. We don't have to mess around with limits and sums and all that good stuff anymore. So what we should do is we should try to find some useful applications now that this thing isn't so difficult to compute. And the first thing we want to try to do is try to compute the average value of something. So, you probably remember from, I don't know, maybe elementary school or something that if you had to compute an average value of the numbers 4, 6, and 10, well, their average means, well, you just add them all together and you divide by the total numbers that you have. And you get some number out and it's all good, whatever it is. So this isn't so bad if you only have, a few things to do. Even if you had 100 things to compute the average of, it wouldn't be so bad. The problem is that many things don't come in these nice discrete quantities where there's just a few of them. Well, suppose we go outside and we measure the wind speed during the day, and we come up with this model here that the average wind speed, or the wind speed during the day, is given by negative 15 cosine of t plus 20, where t is hours since 8 a.m., and speed is measured in miles per hour. How do you go about trying to figure out what the average wind speed was from 8 a.m. to 10 a.m.? So this is a little difficult because let's look at the graph. So the problem with trying to figure out what this average wind speed is the fact that our speed is changing all the time, okay? So even though we took some measurements, it seems like our wind speed is changing nicely all the time in this continuous way. We don't have just like 3 or 4 speeds to add up and divide by 3 or 4. We have here an infinite number of places where the wind speed is changing. It's changing at every single moment here in time. So we need to come up with a way to compute this average, even though it's changing all the time. So how do we add up an infinite number of things? Well, let's think through this. We've done it before. So if you were faced with this problem of figuring out the average wind speed for the first 2 hours here from 8 to 10, what you might do is you might just try to pick some points, add them up, just a few of them, and see what happens. But you'd want to do this very systematically. So what you could do is you could divide our region into n intervals, breaking them up, since it has length 2, we divide by n, so we break it up into a number of even pieces here. So n pieces total, and then at each point you sample the speed. So this will be C1, C2, C3, and we'll do this at n different sample points. And then the speed at each of these sample points will be, well, v of c1, the velocity at c1, the velocity at c2, and so on, the velocity at each point. And now that we have these sample points, what we can do is we can add them all up and divide by the n points that we sampled. So what we have here is we have a nice way to approximate the average by choosing a certain number of sample points, adding them all up, and dividing by how many we picked. However, we know we have a better way to write this. We also know that we can write this pattern using our summation notation, since it's going to be the same thing over and over again, and we've sampled pretty nicely here. So here we're going to introduce some algebraic neatness. What we're going to do is we're going to multiply and divide the whole thing by 2. This is fine because this will just cancel out, right? 2 over 2 is 1, so we can certainly multiply and divide by 2 to introduce this idea here. And next what we're going to do is we're going to do some algebraic rearrangement. So we're going to bring the denominator, the fraction 1 over 2 out. We're going to keep the other part in there. And hopefully what you're thinking is, I know what this thing looks like here. Because what we're doing in here is we're taking our sample point, our sample velocity, and we're multiplying it by 2 over n, the width of the interval. So what does that mean? That means right here what we're doing is we're taking our sample height, multiplying it by the width of our interval. Well, that thing right there, this quantity, is just one of our rectangles. We're adding them all together, adding up all our rectangles. And now the new thing is we're dividing by 1 over the total length of our interval. And what this quantity will do is this will give us a very good approximation. And if we want a better approximation, well, we need to let n approach infinity. We need to use more rectangles. And once we do that, once we use an infinite number of rectangles here, well, what we're going to do is we're going to get a great approximation, and we know that this quantity right here is going to be the same as if we would have just taken our integral of our velocity from 0 to 2, multiplied by 1 over 2, and that will get us our average. So this is the way in which we can find the average of an infinite number of things, by using an integral and dividing by the length of our interval. So this is so important, we're going to call this the average value theorem. So the average value theorem says that if you start with a function that's integrable on the interval a to b, then you can compute the average value by computing this quantity right here. You compute the integral first, and then you multiply it by 1 over the length of the interval. So let's go ahead and do a couple examples. So let's go ahead and try to compute the average value of the following function on the interval. Our function will be f of x equals x squared, and we're going to try to compute the average value from -2 to 2. And here we also have a picture. So this means that by our formula, what this means in our case a is going to be -2, b is going to be 2, and we've already got our function there. So this means that our average value is going to be equal to 1 over 2 minus a -2 times the integral from -2 to 2 of x squared dx. And if we work through this, we see that we're going to get 1/4, and then by the fundamental theorem of calculus, we can put an antiderivative in here, x cubed over 3 by the power rule, and we need to evaluate this at -2 and 2, and so we're going to get 1/4 2 cubed over 3 minus -2 cubed over 3, which, if we run through all the arithmetic, is going to give us 4/3. So what this tells us is that this function, even though it starts up pretty high, comes down low, and goes back up again, on average, it's right around here, around 4/3. This is sort of the average height of the function over this interval. And it's really neat. So it's an average of an infinite number of things. Let's do one more example. So let's go ahead and try to compute the average value of the function g of x equals cosine of x on the interval 0 to pi. And again, I've given the graph. So it might be interesting for you to think, well, what is the average output value? What's the average height of this function from 0 to pi? So you should go ahead and guess, and we'll see if your gut instinct of the average height matches the value we calculate. So again, in this case, what we're going to have is in our case, a is equal to 0 and b is equal to pi. And so the average is going to be equal to 1 over pi minus 0 times the integral from 0 to pi of cosine of x dx. So we get 1 over pi, and now by the fundamental theorem of calculus we have to think, well, what's the antiderivative of cosine? And hopefully you said that the antiderivative of cosine is just sine. And we have to evaluate from 0 to pi. So we're going to get 1 over pi times sine of pi minus sine of 0. And hopefully you remember your trig functions. Sine of pi is 0, sine of 0 is 0, so we end up with an average value of 0. Well, does this make sense? It sure does. This says that from 0 here over to pi, on average, the height here is 0. And this kind of makes sense because all of the heights over on the positive side kind of get canceled out when we take the average with the negative side. So overall, we end up with an average value of 0. This one isn't terribly surprising, right? Because, it kind of looks like they're all going to cancel, but the average value theorem is neat because it works in a lot of other situations as well. So the next application of the fundamental theorem of calculus tells us the mean value theorem for integrals. So this theorem says that if you have a function that's continuous on a closed interval a to b, then there exists a number c in the closed interval ab such that f of c is equal to this quantity, that is the average value. Okay, so what this is really trying to say is this is trying to say, grab yourself a function that's nice and continuous there. Whatever its average height is, well, if you go over to the function, there's actually places where this function achieves its average value. Now, this is not true in the case of discontinuous functions, right? If you had a function here, and this function is not continuous, hopefully you can see visually that its average value will probably occur somewhere in here, and we can see it doesn't actually hit our function anywhere. So you only get your average value out from continuous functions who actually hit them. And the reason this works is basically due to our old friend, the intermediate value theorem. So I'm going to be slightly hand-wavy with why the mean value theorem works, but I think it'll be okay. So suppose we have a function over here given in purple, and we've computed the average value. So the average value of this function is going to occur about there. And we have the interval that goes from a all the way over to b. Well, visually we can see we're going to get the average value, but the intermediate value theorem really tells us why we're going to get the average value. The reason we're going to get the average value is because the average value has to occur somewhere between a place where f achieves its minimum value and where the function achieves its maximum value. And so by the intermediate value theorem, since this function is continuous, what has to happen is it has to hit every single value in between its minimum and its maximum. So this means that it does have to achieve indeed its average value, because the average value is between the min and the max, so somewhere in between we have to actually hit that value. So I understand this is a little wishy-washy here, but that's the basic idea. The average is in between the min and max, so it has to hit it at some point. Once again though, this only works for continuous functions. So let's try out the mean value theorem here with an example. So let's figure out where f of x equals x squared actually achieves its average value on the interval. So the first step here is, well, we need to find the average. And we did this previously. We found that the average value is going to be 1 over 2 minus negative 2 times the integral from a, which in this case is negative 2 to 2 of x squared dx. And previously we did the work here that calculated it to be 4/3. And now we want to think, well, where does this function achieve the value 4/3? And this is as simple as setting your function f of x equal to its average. So in this case, we need to set x squared equal to 4/3 and solve. So what we have is we have x is equal to plus or minus the square root of 4/3, which is just going to be plus or minus 2 over the square root of 3, which if we get out our calculators is going to be about plus or minus 1.1547 dot 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 dot. And so these are the values where our function actually achieves its average value at. So these are interesting values where we actually achieve our average height. And that's pretty much all there is to it for finding these average value places for continuous functions. So our final idea of the day is the net change theorem. So for an example, suppose a particle moves in a straight line with velocity v of t is equal to negative t plus 1 feet per second from 0 to 2 seconds. So let's look at the graph of this function and then we'll think about what this problem is telling us. So what you want to imagine is there's this particle and it sits on this line and it's starting at time 0 at position 0. And then our graph says that as time moves on, it starts out moving at 1 foot per second in the positive direction, but it's going to slow down. So what this means is the particle, it's on this line, it's moving in the positive direction, but it's going slower and slower and slower until at time equals 1, the graph then tells us that at time equals 1 it stops, and then starts moving in the negative direction, faster and faster and faster. So now, this particle, now that it's stopped here, it starts moving backwards. So the velocity is initially positive, the particle initially is moving in the positive direction, it stops, and then moves backwards. And so we want to think, well, what's going to happen if we try to integrate this? What does this really mean? So the integral of the velocity function from 0 to 2 is going to equal the integral from 0 to 2 of negative t plus 1 dt And by the fundamental theorem of calculus, this will be negative t squared over 2 plus t evaluated at 0 and 2. And then we can substitute our numbers in. So let's see what happens. When we put a 2 in there, we get negative 2 squared over 2 plus 2 minus 0 squared over 2 plus 0, which gives us in total, once we run all the calculations, 0. So this doesn't tell us the distance we've traveled. We have to remember that integrating velocity does not give us distance, it gives us position. So different ways to say this that all mean the same thing is it gives us our net distance traveled, which is also known as our current position or our displacement. This doesn't tell us everything our particle has done on its journey here. All it tells us is where we've ended. And so this is an important thing to think about, and we call this the net change theorem. So the net change theorem says that the definite integral of the rate of change of a quantity, so in our example before, f prime represented our velocity, gives the total or net change in the quantity on the interval. So when we take this definite integral, we can use the fundamental theorem of calculus, and it'll give us f of b minus f of a. So what we end up with is not the total distance traveled, but the net change in our position. So integrating velocity will give you net change in position. I really can't iterate this enough. But a really important question is, well, how do we find the total distance traveled instead? So to find the total distance instead, what we want to do is we want to use what's called the total change theorem. So to find the total change in a rate of a given quantity, what we need to do is we need to integrate, very key here, the absolute value of this quantity. What this will do is instead of canceling out positive change and negative change, this will just add up all of the change together. So let's try this out. So if I want to find the total distance traveled by a particle moving in a straight line with velocity given by this function from the interval over the interval 0 to 2, what I need to do is I need to take the integral from 0 to 2 of the absolute value of my velocity function. So this is the integral from 0 to 2 of the absolute value of negative t plus 1 dt. And so if we look graphically, what this means is this means that for the first part of my function it's going to remain the same since it's positive, but then at 1 the absolute value will flip my function upwards. It'll flip it across the x-axis there, and so I'll really be integrating this quantity instead. So what this means is I'm going to have to break my integral up into two separate integrals. The first one will be the integral from 0 to 1 over the positive part of my function, plus then I need to integrate from 1 to 2 the opposite of negative t plus 1, because that negative sign right here is the result of applying the absolute value. It switches the sign, so it takes the opposite, it moves the negative part up to become positive. And so when I compute these, so again, by the fundamental theorem of calculus, I get negative t squared over 2 plus t evaluated 0 and 1, plus by the fundamental theorem of calculus, I take the negative of negative t squared over 2 plus t evaluated now at 1 and 2. And when I run these numbers through, what I end up with is I end up with, for the first quantity, 1/2, and for the second quantity I also end up with 1/2. So overall I get a total distance that my particle moved 1 foot in total. So while if I look at the particle, its net distance was 0, it came back to where it started, overall to get there it moved a foot. So that's it. That was the last big theorem from this section. So as always, try the problems on Blackboard, take your quiz, post a question, and we'll talk more about this in class.